Hi, I'm John Doherty and welcome to another video in the series Nuts and Bolts of using PEST and PEST++. Today we're talking about PLPROC, a parameter list processor. So firstly, what is PLPROC? Well, to discuss PLPROC we really have to discuss what a model does. So suppose we're using PEST or PEST++ to calibrate a model. So I've got a picture of the model here. Now that model has input files and output files, and as we discuss in other videos, this is the way that PEST or PEST++ interacts with the model. This is the non-intrusive interface that it uses to change parameters, run the model, read model outputs. Now in most cases in which PEST or PEST++ is being used to perform operations which support decision making, the model that PEST or PEST++ is running is actually going to be comprised of a simulator plus pre-processors and post-processors. In other videos I refer to this as the model sandwich. Pre-post processors normally perform tasks that have to do with parameters. They're the things that takes the parameters that PEST or PEST++ adjusts and manipulate those parameters and eventually write input files that the simulator can read. At the back end of the simulation process, post-processors read model output files, undertake temporal, spatial interpolation, and then write files containing numbers that are the model-generated counterparts to field observations. PLPROC fits into this sequence here at the front end. It's a preprocessor, a parameter preprocessor. Collectively, this pre-processing and post-processing operations, they comprise the interface of the rather abstract simulator world with the real world. Now, as a parameter preprocessor, PLPROC supports a lot of parameterization devices. This was why it was built, to support a range of parameterization devices that can give us flexibility, the flexibility required to be innovative when we're undertaking real-world decision support modeling. Parameterization devices that it supports are listed here. So, zones of piecewise constancy, pilot points, conceptual points, independent normal deviate subject to 2 and 3D spatial convolution, factors applied to random parameter fields if we're using ENSI for inversion, polylinear features, movable structural overlay parameters, movable fault planes, and all combinations thereof. Now, the supporting of all those parameterization devices requires some fairly complex numerical operations. So, in order to provide that support, PLPROC can undertake a lot of parameterization pertinent tasks. These include, as we'll discuss, things such as anisotropy-aware spatial interpolation using kriging, inverse power of distance, radial basis functions, vertical layer-based interpolation, blending of hydraulic properties between structural features and host material, construction of covariance matrices based on spatially varying variograms, random parameter field generation and manipulation based on stationary and non-stationary geostatistics, and arbitrary mathematical operations between the various spatial entities that it supports. Part of the design philosophy of PLPROC is that, like PEST, it has a model-independent interface with its simulator. So we can do all these things regardless of the simulator that we're using to simulate groundwater processes. So, as we'll see, it can interface with a simulator using template files, but more complex template files than those which PEST and PEST++ uses. So, but apart from being model independent, part of its functionality allows a fairly seamless interface with a particular family of models, these being the ModFlow family of models. So that's an overview, a very quick overview of what PLPROC does. Now let's dive a little bit deeper. Because of the complexity and the number of operations that it performs, PLPROC receives its instructions through scripts. A script can be recorded in a text file. This can be done using a text editor. And the scripting language that PLPROC uses has much in common with any other programming language. So a script file can include comment lines. It can include continuation characters so that a script element can continue from one line to the next. Most PLPROC functionality is accessed through its functions. We'll talk about these shortly. Functions are highlighted in red in this picture. Functions have arguments, which are highlighted in green. PLPROC uses entities, sort of like objects. We'll talk about them. And these objects feature in the function arguments. They can also feature in equations for which arbitrary mathematical manipulation can be performed between the objects which PLPROC uses. Special equations can feature in its function calls. These allow the operation of the function to be restricted to certain segments, certain parts of the entities which feature in those functions. To run PLPROC, you just type its name at the screen prompt, followed by the name of a file that contains a PLPROC script. Let's call it plproc.dat. When PLPROC is run in this way, it reads the script. Then one by one it executes the statements that are found in the script and reports what it does to the screen. If there's any problems, it'll provide a comprehensive error message. When it's finished undertaking all the operations that were requested of it, it'll tell you, and that's the end of the PLPROC process. Alternatively, PLPROC can be run just by typing its name at the screen prompt. In this case, it asks for the name of the script. It then reads the script, and then just as before, it undertakes all the operations that it was asked to do through the script and reports the end of the process to the screen. Now, let's dive even a little deeper and look at the entities that PLPROC supports. Now, things are going to get a little bit complicated here, and we're going to go into some detail, and we're going to look at the details of some function calls. There's far too much to remember here, and it could get a little bit boring. I suggest you play this video at 1.5, this normal speed. My intention here is not to give you a complete instructions of how to use PLPROC. My intention is to give you an overview of all the things that PLPROC can do so that you can be aware of what it does, and if you like it, you can use it and then find out more details in the comprehensive PLPROC manual. So the first entity that we'll look at, and probably the most basic PLPROC entity, is the C-list. C stands for coordinate, and a C-list is a list of points, well, a list of point coordinates. Each point can have a name. We can give it the name, or PLPROC can name each point internally just in a sequential manner. So, a C-list, points, label, and 2 or 3 coordinates, depending on whether the C-list is 2-dimensional or 3-dimensional. So a C-list can represent a 2-dimensional array of pilot points, a 3-dimensional array of pilot points, the segments of a polylinear feature, and very importantly, the centers of cells of a structured or unstructured model grid. A C-list can be created in a variety of different ways. It can be created by reading the details of that C-list from an external file. Now in this and other pictures, the name of the pertinent function is highlighted and italicized. So we can read C-list specifications from an external data file, an external ASCII or CSV file. They can be read from a structured grid specification file. This is a text file which is easily prepared using a text editor. More complex grid specification files provide the specifications for a ModFlow USG grid. PLPROC can read that. PLPROC can also read a ModFlow 6 binary grid file, which is written by ModFlow 6 to obtain the specifications of the grid. Now, if a CList is created using any of these functions, then the relationship between the CList and the ModFlow grid specifications are pretty intimate, and this can be used to advantage later when writing input files for these types of models. Using PLPROC, you can create a three-dimensional or two-dimensional structured grid just in PLPROC space, and that can be the basis for creation of a CList. CLists support these entities called G-planes, which are two-dimensional features which can have any orientation in space, and they can be heterogeneous, so a two-dimensional CList can be defined on their surface. CLists can be created by new CLists can be created by partitioning existing CLists. And using seglist functionality, which we'll talk about later on, CLists can be created from seglists. So that's CLists in a nutshell. Now let's talk about SLists. S stands for selection. SLists are kind of children of CLists. So here's a CList. An SList is simply a list of integers, with each integer associated with each element of a CList. A CList can support many SLists. We're just illustrating them here. So, how do we create an SList? Once again, there's a variety of ways. The easiest way is just to assign all numbers, all elements of a CList a single integer. That can be done using the new SList function. An SList can be created from a plist. We'll see plist shortly. The elements of an SList can be defined by reading the contents of an external file, including a CSV file. The elements of a SList can be defined by reading a ModFlow compatible integer array. Some SLists can be created using these special CList creation functions, in which SLists are also created. For example, the SList may refer to the layer of each cell in a ModFlow USG or ModFlow 6 grid. And there are more complicated ways to build SLists, for example by assigning a particular value to elements of one SList based on spatial proximity to elements of another SList. The SLists do not need to share the same CList. And even more complicated, something we'll touch on later, is that when we want to write an input file for a ModFlow type model. Now, as I said a moment ago, if we create CLists in certain ways, then the relationship between elements of a CList and cells of the model grid is known. We can ask PLPROC to read an input file for a ModFlow or ModFlow USG or ModFlow 6 model, and if this input file contains tables of cells, we can ask PLPROC to identify the cells that it finds on those tables and record what it finds in an SList. So that's SLists. Now let's move on to PLists. A plist is like an SList. However, instead of being comprised of integers, it's comprised of real numbers. Many PLists can be associated with a parent CList. A plist can be created using a simple function call where every element of a CList is assigned the same real number. That's the easiest way to create a plist. Its specifications, the values assigned to each plist element, can be read from an external file, including a CSV file. Elements of a plist can be informed by reading a ModFlow compatible real array file. If a CList is created using this special function call that allows reading of a ModFlow 6 binary grid file, then the elements of a plist are created automatically containing the cell bottoms, the elevations of the cell bottoms. Plists can feature in equations. If a plist is featured on the left side of an equation and it doesn't exist before, it is defined through implementation of that equation. However, the thing about plists is that they can be used in much more complicated ways than we've just seen, and I'll illustrate what I mean through a picture. Suppose we've got a CList, a source CList I'm going to call it, and this can be comprised, for example, of pilot points. This may represent pilot points. And suppose I've got another CList, a target CList. This can be the elements of a model grid. Many PLPROC functions support informing elements of a target CList by elements of a plist pertaining to a source CList where the source CList and the target CList are different. So, the source CList may contain many child plists and SLists. The target CList may have its own child plists and SLists. A PLPROC function, such as spatial interpolation, will allow the filling of this plist or part of that plist by the elements of this plist or part of that plist. The operation of that function can be restricted to certain elements of the source CList and certain elements of the target plist. So let's have a look at some of these functions. So in this first function, plist elements are assigned by element association criteria such as commonality of SList element values. This is simply zones. We can directly assign elements of one plist on the basis of spatial proximity of elements of another plist, regardless of whether or not they have the same parent CList. More sophisticated operations based on spatial proximity allow blending of the elements of one plist with another plist. We can combine plists using factors. So realizations of plists, random realizations of element values housed in plists can be combined using factors which we supply. This can be useful for doing things like ENSI inversion. I mentioned a G-plane before, a movable two-dimensional structural feature containing its own CList. Elements of plists associated with that CList can inform a background model grid through complicated blending operations based on proximity of elements. Other PLPROC functions allow us to do interpolation based on pre-calculated interpolation factors. We'll come to that in a moment. Blending again, in this case not from a G-plane but from polylinear segments which may transect a model grid. The elements of the parameters assigned to the polylinear segment can then inform the background grid through a blending operation specified by the user. PLPROC undertakes inverse power of distance interpolation in 2 and 3 dimensions, but it does this in a way where anisotropy can vary in orientation and magnitude throughout a model grid, so it's anisotropy aware 2 and 3 dimensional spatial interpolation. PLPROC can undertake interpolation once again, taking into account of anisotropy and possibly spatially variable anisotropy, this time using radial basis functions. A more simple element of plist value transfer is simply copying a block of plist elements from one part of a plist to another part of the same or different plist. PLPROC can undertake vertical interpolation from one layer of a model grid to another. These may be part of the same or different plists. Linear interpolation is undertaken. This can be based on elevation or layer number. I mentioned calculation of interpolation factors a moment ago. Interpolation factors can be calculated a number of ways, including kriging. And PLPROC provides access to a number of ways of doing kriging. It can be based on a number of different variograms. The variogram can vary in space, if you like. Interpolation can be two-dimensional or three-dimensional. The variogram can be calculated automatically by PLPROC, if you like. And once again, this can be anisotropy aware, and anisotropy can change in different parts of the model domain. One specialist PLPROC function allows interpolation down a narrow alluvial valley where anisotropy can change in accordance with the direction of the nearest boundary of the alluvial system. Still other PLPROC functions undertake spatial averaging or 2 or 3D spatial convolution. This allows creation, the filling of a model grid with a random hydraulic property field in which the geostatistical properties can differ from point to point throughout that model grid. Parameter fields can be generated in a random fashion, and or they can be adjusted using other PLPROC functions. So that's a very quick coverage of all the things that can be done using plists. Now let's look at another entity, the seglist. A seglist is normally used to represent complicated polylinear features such as a stream. It's normally used to conduct operations which can inform properties of the stream, such as perhaps its conductance. So associated with each seglist are elements of a C-list. C-lists then host P-lists, which are devices through which parameterization of the seglist is implemented. So, first, linear interpolation is conducted down this complicated polylinear feature, regardless of how complicated that feature is. This is done by some PLPROC functions. Other PLPROC functions then allow direct transfer of the properties of the complex polylinear feature to underlying model cells. This can be done either directly or through a blending operation. So, function readSegFile reads the specifications of a complex polylinear feature from an ASCII text file. C-lists can be associated with the seglist in a variety of ways. Interpolation factors down the polylinear feature, and then the blending operation with the underlying model grid is performed using other PLPROC functions. Another type of polylinear feature is the structural overlay parameter. Structural overlay parameters are discussed in another video. This is a polylinear feature, but normally much less complicated than a seglist. It might only have a few vertices that are used to define its shape. A structural overlay parameter might be just a linear feature, a polylinear feature, or it may be polygonal. Now, interpolation can be conducted down the polylinear segments which comprise the feature or within the feature. This is undertaken by certain PLPROC functions, and then interpolated values can then be blended with the properties of an underlying model grid, that is a P-list belonging to a model grid C-list, using other PLPROC functions. An important property of structural overlay parameters is the fact that they can move. The vertices of a structural overlay feature can slide along elements of a user-described C-list. So individual vertices of the structural overlay feature, as they slide along these sliders, the feature can change shape. And the entire feature can move along another C-list. So the feature can change shape as it moves, all on underlying sliders defined through C-lists. PLPROC can be used to define covariance matrices. These are often assigned to pilot points. Covariance matrices can be based on 2- or 3-dimensional variograms, and these variograms, the properties of these variograms, can vary in space. The covariance matrix that is thereby defined can be used for regularization or for random field generation. Here's a function that undertakes random field generation for a set of pilot points based on a previously created variogram. Random field generation can be pretty clever. So, for example, the elements, the values assigned to pilot points may be conditioned based on the values, known values at certain pilot point locations. Finally, the final element that PLPROC uses, the final entity, is the scalar. And as the name implies, a scalar is just a single number. The name of a scalar, the values of scalars can be read from an external scalar file. Scalars can be used in PLPROC function arguments and in PLPROC equations. In certain circumstances, it may be good to build a template file for this scalar so that PEST can estimate the values of these scalars during an inversion or uncertainty analysis process. This can affect the way that PLPROC functions are done, so that randomness associated with perhaps unknown aspects of a prior probability distribution can be incorporated into an inversion or uncertainty analysis process. Because PLPROC does a lot of complicated things, there's ample room for user error. So PLPROC provides primitive reporting and debugging functionality. PLPROC can record the time it takes for operations. It can write files in which it reports the existence of all created entities, and files that can contain values associated with those entities. So you can make sure that it's doing what you expect it to do. As I mentioned earlier, an important design criterion for PLPROC is its ability to write to simulator input files in a model-independent way. So here's our simulator, and it has its set of input files. And these input files have protocols that are established by the simulator. So, for example, if we're looking at a ModFlow model, some of its input files may require that data be provided in lists. So here we have some columns which identify cells of the model, and here are properties, parameters associated with those cells. Other input files simply contain arrays of data. Now PLPROC uses template files to write these model input files. However, these template files can be a lot more complicated than the template files that PEST uses. They can include embedded PLPROC functions that can allow recognition of these elements, and then so PLPROC knows what values to write to these other columns based on the linkage that exists between model elements and elements of a PLPROC C-list. Recall that these linkages can be established if a C-list is defined through reading a grid specification file that is pertinent to a certain model type. So, using this embedded function, PLPROC can read these elements and write pertinent values to the model input file. Embedded functions can be used to write arrays of values as well, but this is normally easier. So the function which PLPROC uses to write a model input file is, unsurprisingly, called write model input file. Here's the name of the input file that must be written, and here's the name of the template file that's used to write it. There are other ways in which PLPROC can capitalize on this linkage between C-list elements and model grid cells. Another one of its functions, which I've already mentioned in fact, can pre-read a model input file to find out what cells are cited in data tables that exist within that input file. It can then tailor its writing of that input file according to the cells that it discovers. In this case, it may read an existing model input file and write another in which the values of elements in certain tables have been filled or manipulated from these existing values in writing the new model input file. See the PLPROC manual for further details. Sometimes the writing of input files is easy. For example, other PLPROC functions allow the recording of a matrix to an external file. Others allow recording of all or part of P lists and S lists in columnar or data files or CSV files. So that's it really. That's PLPROC in a nutshell. As I hope you can see, PLPROC was written with the needs of highly parameterized calibration, uncertainty analysis, predictive hypothesis testing, and other important tasks required by decision support modeling. It was written with all of those in mind and trying to give you, the user, the ability to do these tasks, to perform these tasks in innovative ways. PLPROC is an important component of the model sandwich. It has a comprehensive manual which describes in detail all of the functionality that I've referenced in this video, and it can be downloaded free of charge from the PEST web pages. So that brings us to the end of this video, and thanks for listening.